Section 3 of the circles unit is going to start digging more deeply into circles and some of the special segments and relationships that happen inside of circles. So we are going to start with the perpendicular bisector theorem. Now we've seen this theorem before, and it talks about having that perpendicular piece right here and bisecting. Now from previous units, we know also that those guide wires from a point on the perpendicular bisector to the end points of the segment, that they are equal. This should make perfect sense because this segment OA is a radius the same as OC, the same as OB. And so all of these pieces begin to kind of meld together. And you see, as soon as I draw that radius OA in, then I have a right triangle. And as soon as I have a right triangle, I can employ the Pythagorean theorem. I can employ triangle sum adding up to 180 to find angles. So lots of different ideas begin to be layered when we start talking about these things. So what does it actually say as far as circles? It says a diameter or radius of a circle is perpendicular to a chord if and only if it bisects the chord and its arc. And again, this is an if and only if situation. If you know that you have a perpendicular radius, then you get bisected chord and arc. That's another important part, is that this arc and this arc are also equal. If you know that you have a bisected chord and arc, then you get that you have a perpendicular radius. Okay. Very important theorem, something that gets used a lot. If we talk about the congruence chord theorem, it says in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. That's where this comes in. If they are equidistant from the center, then the chords are congruent. So again, if you know equidistant from center, then you get equal chords. Conversely, if you know the chords are equal, then you get that those segments between the center and the segment are equal. Then you get equal segments. So a pretty powerful theorem because, again, I could draw in a triangle. And then interesting things can start happening with my triangle properties. Parallel chords theorem says, in the same circle, parallel chords, if I know that AB is parallel to CD, then I know they intercept congruent arcs. Then I can conclude that they're going to slice off the exact same amount. And that should feel really good in your gut. So if you know chords are parallel, you know the arcs they create when they intercept the circle are also equal. So let's look at some examples. And I would say of all the examples, this one is super, super important. So given circle Q, W to X, right here, is 10, and the arc is 150. So WPR, so this arc right here is 150. So, you know, just for curiosity and for fun, if I drew angle as an aside, we know that angle WQR is equal to 150 because that's the central angle that makes that arc, and we talked about that in the last section. So finding W to P, if we remember that perpendicular bisector theorem, this is perpendicular, it is bisected, it bisects the arc. So that means the arc is 75. Now, WR is this piece right here. It's a perpendicular bisector. We're talking about 10 plus 10, so its length is 20. Now, where things get really interesting and we start combining our different sections is if we are looking for QX. Well, where is QX? QX is right here. Well, that little piece right there, I don't know that that radius is bisected, and that is a big mistake kids make. But if I look at this figure right here, I have a right triangle. Now, you might be thinking you don't have enough information because it doesn't appear that you know QW. But you do know QW because that ends up being, you can find it rather, it's a radius of QP, it's the radius of QR. So they give me that this is 5, I don't know the radius, I know this one, and I can solve. So I'm going to go ahead and draw my triangle out so it's a little bit more clear. And the thing is, as long as you are solving for a radius, QW is the same as QP is the same as QR. So don't be tricked about what you can or can't find or do or don't know. When all of those radii, no matter where I draw a radii in, it's the same. So I can use any one of those values to determine the length of the radius, which is what they're asking me to find, is really what is the length of the radius. So I'm going to use QW. So this is Q, W, and X. They give me QX is 5. I know that XW is 10. This is my radius. The radius is the hypotenuse, and my old friend Pythagorean Theorem comes into play. And I can go ahead and write that r squared is equal to 5 squared plus 10 squared. So r squared is 125. Take the square root of both sides. R is the square root of 125, or approximately 11.2 units. Now you know that you did it right when 11.2 is bigger than your other two measurements because it is the hypotenuse. It should be the biggest side. Now this next example is a little bit more of a thinking example than a calculating example. So I'm given circle Q and I'm given that chord SR is equal to chord TU. And because of the arc chord theorem, which says that if equal arcs, equal segments, chords, will cut off equal arcs. So then I know this to be true simply by that. Additionally, we could go on and say that angle SQR is equal to angle UQT because they're central angles with equal arcs, which means the angles are equal. So lots of ways to find equal pieces. If you can find equal pieces, then you can write an equation. Let's look at one more example. Given that this arc and this arc are equal, find x. This is a matter of vertical angles. Everything is lining up. If the arcs are equal, I simply set the expressions for those arcs equal to each other, add 27 to both sides, divide by 2, and x is 55. So go ahead and try the practice problems that follow the quiz and tune in for part 2.